Derek, I can't see this time rolling out on the top right. Can you see the slides? You see the time is not rolling out on the top right.
Yes, it is.
It is rolling out?
Yep.
Okay. Okay, good morning, everyone. Welcome to this special interest group session on STAAD Pro. Today's session is on application of cables. Before I start this tech talk, I would like to I would like you to answer these questions, poll questions. Does any one of your projects have cables? Please submit this answer. I'll give you a few seconds for this. Okay. Let's see the results. 59% of you say yes, you have cables in your projects, and 41% say no. Okay. Let's move on to the next poll. Have you ever used a non-linear cable analysis in STAAD Pro? That is the command perform cable analysis. Please answer yes or no. I'll give you 10 seconds for this. Okay, let's move on to the next. Let's move on to the results. So only 13% of you say yes. Remaining 86%, 87% say no. Okay, so that means this session, I chose the right topic to explain about this non-linear cable analysis. Okay, have you used linear cable analysis feature in STAAD Pro? This is the next poll. Please answer this. The linear cable analysis just uses the member cable command and perform analysis command, not the perform cable analysis. So this is useful for simple structures with cables. So I believe many of you might have used this feature in the past. If not the non-linear cables, at least the linear cables. So please answer this poll. I'll give you 5 more seconds for this. Okay, let's see the results. Again, only very few of you say yes. 16% only say yes. Okay. Okay, that's good. So that this session will be useful for you. Okay. So, topic for today is applications of non-linear cable analysis. My name is Madan Elmalai. I am based in the Singapore office of Bentley. A recommended prerequisite for attending this special interest group session for STAAD Pro is that I would suggest you to watch my presentation on April month this year. The topic is applying load groups in STAAD, because both load groups and non-linear cable analysis are very much interrelated. I'm sure at least 90% of the attendees here have attended that session on April. If some of you have not attended it, the recordings are available in our Bentley website. Look for the events menu in Bentley website and look for on-demand webinar content and search for this applying load groups instead. Okay, so this is a recommended prerequisite for attending this session. Okay, the agenda for today is introduction to cable structures, and then we'll look at the 3 methods of cable analysis available in STAAD Pro. And then we'll learn more about linear cable analysis with an example on guide mast. And then we'll look at the non-linear cable analysis and 4 examples on various type of cable structures. And then we'll conclude with a question and answer session. Okay. So cables, as all of you know, find applications in many type of structures. such as tension rods in steel structures, guide masts, as in communication towers, cable stayed bridges, lifting slings for lifting platforms on offshore projects or oil and gas projects, cable supported roofs, tension rod system, and many, many more. Hence, understanding the proper modeling of cables is important. Cables by nature are geometrically nonlinear because they sag in compression and stretch in tension. Even though cables are nonlinear in nature, we can still approximate the nonlinear nature of the cables into a linear cable up to a certain extent, provided the structure is simple with few cables only. When the deformation of the structure is large, or when there are many cables in the structure, or if the geometry is of catenary cable, it is recommended to use the nonlinear cable analysis. Okay? So these are the three cases largely we can summarize where we can find the application of nonlinear cable analysis. When the deformation of the structure is large, or when there are many cables in the structure, or when the geometry is of a catenary cable. A catenary cable, I mean, is a curved profile of a cable. A cable, when it sags, for example, a horizontal cable, when it sags due to self-weight, you can see the curved profile of the cable. So that needs this nonlinear cable analysis. So here are some examples of cable structures. You can see guide mast and cable roofs, cable membrane sheeting roof, and a bridge, cable stayed bridge, and a multi-point lifting, and a roof, a stadium roof connected with cables. So the roofs will be subjected to gravity load as well as lateral load. So hence the cables has to withstand both the gravity and lateral load. So you need to do nonlinear cable analysis for all these kind of structures. Coming to the three methods of cable analysis, STAAD supports linear cable analysis, nonlinear cable analysis, and also a third method called advanced cable analysis. The third method, advanced cable analysis, requires the STAAD Advanced license. Okay, for this session today, we'll cover the first two topics, the linear cable analysis and nonlinear cable analysis, and maybe some other day we'll look at this advanced cable analysis. Okay. So first, let's have a look on linear cable analysis before we have a look on nonlinear cable analysis. Okay. In the linear cable analysis, the cable members are used with perform analysis command. Okay, just like a normal structure, we use perform analysis command, a linear static or linear elastic analysis, and the cable members are declared as member cable. Okay, so this linear cable analysis is suitable for structures only with few cables. Okay, stretching of cable is considered in this analysis, suitable for small deflections. In addition to member cable command, you also have to use the member tension command. This is to avoid the cable members taking compression. Repeat loads or load groups should be used for combining the loads. I already explained this, the purpose of load groups in my previous tech talk in April. Let's have a look on the limitations of the linear cable analysis. The linear cable member is only a truss member whose properties accommodate the sag factor and initial tension. Note that the cable member by default in STAAD, a linear cable member, is only a truss member. It is not a tension member. So some users complain that when they specify the cable member, they see that the member is taking compression also. The reason is because they forgot to specify the member tension command also. So when you perform linear cable analysis in STAAD, the cable member has to be declared as member cable in addition to member tension command. Okay, this is to avoid the cable member taking compression forces. Okay, so this is a limitation in the linear cable analysis in STAAD. Also, the linear cable analysis can't handle large deflection. For example, lifting analysis without lateral support. Many users I have seen, when they perform the lifting analysis of a platform using some slings and spreader bars in STAAD they use some fictitious lateral support to avoid instability when they do the analysis. And this fictitious lateral support doesn't exist in the site. So they do some iteration to make sure the support reaction they get for this fictitious lateral support is 0 or close to 0. So this is a trial and error approach. Okay. And another important limitation of this linear cable analysis is that it can't handle catenary cables, the cowed cable profile as in the cable straight bridge. Also, this linear cable analysis can't handle models with large number of cables connected to each other. For example, tension rod system, cable straight bridges, etc., etc. Let's have a look on this first example on guide mast for linear cable analysis. For some reason, I can't able to see this video, but I'm sure all of you are able to see the video. Just a minute, let me try replaying it. Sorry for that. Give me a minute. Okay. Sorry, again. Okay, so on the screen you can see a guide mast, approximately 54-meter tall. So you can see 3, 6, and 9 cables. So this is a good example of a linear cable analysis. Okay, having very few cables and the deflections you can expect is small. And here you can see the platform on the top. The platform is made of channel sections. Okay, that is a bending member. Otherwise, all other members in this model is either a cable member or a truss member. Okay, so the tower consists of mainly truss members. They are single angles, and the platform is where the cable is connecting. That is made of channels that is connected to the cables. And the cable itself is a 30 mm rod. Okay, so you can see the cable is declared as member tension as well as member cable, and all the members in the tower is declared as member truss except the platform. Support, we have pin support. Load cases, you can see I have used load groups in this model, the reference loads. And then I call those reference load in my load cases, primary load cases, dead load, wind load on appurtenances. And then a few combinations using the reference load. Note that I have not used load combination command to combine the loads. I use reference loads to combine the loads. And this is the input file. Here you can see I have used some groups. You can see the member truss, member tension. I used initial tension on the member cable as 7 kilonewton. This you can use whatever initial tension that you can achieve at the site. You can use any value here. You can even put negligible values like 0.1 kilonewton or even 0. I'm sorry, this example I used repeat loads, not reference loads, okay, because it's a simple structure. But doesn't matter whether you use reference load or repeat load, you get same answer. Okay. You can see I got some zero stiffness warning messages. This is because at many locations the cables are connecting to either a pin support and another cable, and for example, the ground supports. You see the cables are all connecting to the pin support. So that is a point of zero stiffness. And also a truss member connecting to another truss member without any frame members. That is also a point of zero stiffness. You usually get a zero stiffness in the direction of 4, 5, and 6. 4 being mx, 5 being my, and 6 being mz. So you can see this point, highlighted point, you see all the members are truss members. Okay, so there you definitely get a zero stiffness warning message. So to suppress these warning messages, I use setprint1 command. The setprint1 command will suppress this warning message. After you have gone through the warning message clearly and understand this warning message clearly, then only you use this setprint1 command to suppress the zero stiffness warning messages. Okay. Note that our model doesn't have any instability warnings. It had only zero stiffness warnings. And now you can see in the output file, it is free from any zero stiffness warning message. All you see is some notes about the convergence of the member tension command. Now let's have a look on the output file. The post-processing. You can notice the deflection, the maximum deflection is 154 millimeter. Now we can plot the axial force diagram. You can see the blue color members or tension members and the brown color members or compression members. So instead of a diagram, we can now color code it so you can clearly see the tension and compression members. Except the cables, almost all the members in the tower is having compression. So here you can see the maximum axial forces, maximum minimum. We can filter to only our cable members so that we can see how much tension, maximum tension in our cable. That is 11 kilonewton tension on the cables. So you can see there's no compression on this cable member, only tension. Okay. Okay, so let's see the comparison of results for the guide mast. You can notice that the maximum deflection is 154 millimeter. Either we use load grooves or repeat loads. The results are same. When you compare the deflection or maximum axial force or maximum support reactions, the results exactly match whether you use the reference load or repeat loads. Okay. Some of you may be aware that the reference loads got a new name called load groups in the physical modeler, starting from STAAD Pro Connect Edition. The analytical modeler still calls it as reference load, but the physical modeler in STAAD Pro calls it as load groups. Okay. So when I say load groups, it is reference loads. Okay. But see the same model, when I analyze it as load combinations, you can see the results are changing drastically. Okay. Absolutely wrong results. You can see the maximum deflection, the difference in results is 12%. The axial force, maximum axial force difference in results is 42%. And the support reactions difference in results is 80%. Okay. So with this small example, you notice that you should not use load combination command for structures having cable members, member tension, nonlinear analysis, P delta analysis, spring compression, spring tension, etc., which I already explained in my previous tech talk in April on load groups, applying load groups. Now let's move on to the next topic, nonlinear cable analysis. In nonlinear cable analysis, cables are used along with perform cable analysis basic command. Okay, so instead of the perform analysis command, we should use the perform cable analysis command. And when you do not have the STAAD Pro advanced license, by default, it will automatically add this basic command. Okay. Later on, I'll explain you the dialog box. Okay. So when all of the members, elements, and support springs are linear, except for cable and or preloaded truss members, then this analysis type may be used. Okay. That means, except the cables, all of the members in your structure are still linear. It's just the cables alone are treated as nonlinear. Okay. So this analysis is suitable for large deflections. This method assumes small displacement theory for all members, trusses, elements, other than cables and preloaded trusses. Repeat loads or load groups should be used for combining the loads. You should not use load combinations. Load combinations will give wrong answer for nonlinear analysis. Let's have a look on the advantages of this nonlinear cable analysis. This analysis can handle large deflections. Example is lifting analysis without a lateral support. We can analyze lifting analysis by using this nonlinear cable analysis without using a lateral support, and can calculate the sway, the deflection of the platform when you're doing the lifting. And it can also be used for catenary cables. And this analysis can handle complex structures with many cables interconnected to each other, like tension rod system, cable stayed bridges, etc. This is the command syntax for basic nonlinear cable analysis. Perform cable analysis, basic, steps, EQ iterations, EQ tolerance, sag minimum, stability, and K small parameters. So there are totally 6 parameters, starting from steps till K small. And out of the 6 parameter, the 2 parameters which are highlighted in green color are the most important, sag minimum and stability. And notice that the stability parameter has 2 inputs, F5 and F6. Okay. So let's have a detailed look on these parameters. The first parameter is steps, F1. The user inputs is F1, the number of steps. Okay. The default is 145 number of steps. I highlighted in yellow color because most of the times, for most of our problems, this default value is good enough, but not always. Let me explain more about that. So this steps is the number of load steps. The applied loads will be applied gradually in this many steps. Each step will be iterated to convergence. If entered, the value should be in the range of 5 to 145. Okay, so the load applied will be, the load you input will be applied in this many number of load steps. And the default value is 145. For small models, this 145 load steps is good. But when we are analyzing very large structures like a cable stayed bridges, which consist of hundred thousands of members and 10,000s of members, then this will take enormous time for analyzing. So for large structures, you can start playing with this value, reduce it to say 5 or 10. Okay. Whereas for small structures, leave it to the default 145. So that's why I highlighted it as yellow color, because for most of the models, You don't have to touch this value. You don't have to change it. Leave it to the default, except for huge models where you need to reduce it to a lower value to reduce the analysis time. The second parameter is EQ iterations, F2. Maximum number of iterations permitted in each load step should be in the range of 10 to 500. Okay, the default value is 300. For most of our problems, this EQ iteration default value of 300 is good. So we don't need to touch on that, except for some special cases where we may need to increase this value to 500. Okay. So that's why I highlighted it as a green color, because most of the time you don't need to modify this value. Same as the third parameter, EQ tolerance, the convergence tolerance for the above iterations is 0.0001 in length units. Okay, which is already a very stringent tolerance. So the default value we don't need to change. Okay, so that's why these parameter 2 and 3, EQ iterations and EQ tolerance, you can very much rely on the default value. That's why I put it on green color. Next, the fourth parameter, Sag minimum. This is the most important parameter. Sag minimum. Cables may sag when tension is low. All of us know this. This is accounted for by reducing the E value, the Young's modulus value. Sag minimum may be between 1 and 0. 1 means no sag E reduction. 0 means full sag E reduction. The default value is 0, which I again put it as yellow color because this default value is not good. Many times we have to change this. Okay, so that is the most important parameter, sag minimum, to take into account the sagged cable member, the stiffness of this sagged cable member. Okay, default is 0, the maximum is 1. Usually I start with a value of 0.5, and if that doesn't help, I use 0.6, then up to 0.7, 0.9, and 0.9, up to 0.9. Okay. Let's move on to the next parameter, stability. This has two parameters, F5 and F6. Stability is a stiffness matrix value, F5, that is added to the global matrix of each translation direction of joints connected to cables for the first F6 load steps. The amount added linearly decreases with each of the F6 load steps. If F5 is entered, use 0 to 1000. If F6 is used, use 1 to 145. Okay, this parameter alters the stiffness of the structure during the initial iterations only. Okay, to put it simple, this stability parameter is an artificial stabilizing stiffness matrix. Okay, this value is input by the user in the range of 0 to 1000 force per length units, depending on the unit that you use in your model. It's like a spring unit, force per length. The default value for F5, this stability is 1. Okay, for example, if our model is using a unit of kilonewton and meter, then this F5 value of 1 is 1 kilonewton per meter. Okay, and F6 is this 1 kilonewton per meter will reduce to 0 in F6 steps. Okay, the default for F6 is 1, which is not good. That's why I highlighted in red. Okay, so usually I use the maximum value 145 for small structures, whereas for big structures I may use a value of say 10 or 5, depending on the size of the model. Okay, but for small structures, I'll use a 145 value for F6 parameter. Okay, and K small is also same like stability parameter. It is also an artificial stabilizing stiffness matrix, but the difference is this is a permanent stiffness matrix. This is a permanent spring that doesn't get to reduce to 0 like a stability parameter. Okay, so K-small parameters permanently affects the stiffness of the structure. That's why if you see the range for F7, the K small parameter, it is between 0 and 1. The default is 0. Okay, which is good. That's why I highlighted in green color, because this is a permanent spring that is not going to reduce to 0 at the final iteration also. So it's going to affect our stiffness of a structure, and this doesn't exist in the site. So don't use it until there is no other go. Okay. 90% of the problems involving cables can be solved just by using the two parameters, sag minimum and stability parameters. On complex models only, we start using the K small parameters as well as other parameters. Okay. So hope you have a clear understanding about this parameters. Okay. Out of the 6 parameters, the most important parameters are sag minimum and stability parameter. This is a frequently asked question: how to arrive at the values for all these parameters? The answer is there is no direct way to find the values of the parameters. If the default values fail, then try sag minimum 0.5 first. If that doesn't work, I try 0.6, 0.7, and then 0.8, and even 0.9. If any value works, then reduce it halfway to the last one that failed, and then rerun the analysis. If the 0.8 value or 0.9 value also doesn't work, then I start trying using the stability parameter of 0.1 with 145 steps. Then keep increasing the 0.1 value until it works. If this fails at about 95% to 100%, then only try the K small parameter of about 0.1 times the last stability value that you used. If it is allowed, try increasing the tension in the member cable command. Okay. It may sound a little bit confusing at this point of time. To make it simple, I would just suggest you to first try with the default values of the perform cable analysis, and if the default values doesn't work, then start using the sag minimum parameter. Start with 0.5 until 0.9. If that doesn't work, in addition to the sag minimum parameter, start using the stability parameter from 0.1 to whatever value it works with 145 load steps. Most of the problems will get solved with this stability parameter and sag minimum parameter. With little bit of experience, you can easily decide the values. Only on rare cases, complex models, the stability parameter, even though when used up to 1000, may not solve the problem. Then when the iteration fails at about 95 to 100%, then only start using the K small parameter. Remember that the stability parameter doesn't going to affect the stiffness of the structure at the end. Only during the initial iterations, the stability parameter is used and is going to reduce to 0 at the 145th load step. Whereas K small parameter is a permanent spring, it's a permanent stiffness matrix. It doesn't get to reduce to 0. So you have to use the K small parameter carefully. Okay. And as much as possible, if it is possible to increase the initial tension in the member cable, you try to increase it so that the analysis will converge faster. Okay, now let's have a look on these 4 examples on nonlinear cable analysis. The number 2 example is again a guide mast, or the same guide mast which I solved using the linear cable analysis. I'm going to compare the results of linear cable analysis and nonlinear cable analysis for the same model. And the second example is a catenary cable, the curved profile of the catenary cable. And the third example is a lifting analysis of a platform. Okay, and the fourth example is a tension rod system. Okay, having a lot of cable members connected to each other. Okay. Okay, so let's have a look on this example 2, guide mast nonlinear cable. Sorry, just a minute. I push on the video. Okay. So you can see on the screen the same guide mast, which I used to explain the linear cable analysis. You can see the load cases. Loads are modeled, the load combinations are modeled using repeat loads. And you can see each of these load cases is separated by perform analysis, cable analysis and change. And this is the dialog box perform cable analysis. And these are the 6 parameters you can see at the bottom. The advanced cable analysis is available only for STAAD Pro Advanced license, whereas the basic perform cable analysis is available for the basic users of STAAD Pro. Here you can see the input file. I use setprint1 to suppress the zero stiffness warning message. I also use the set note off to suppress the notes message also. I noticed that since we are doing a nonlinear cable analysis, I inactivated the member tension command, and I retained the same initial tension of 7 kilonewton. And see the perform cable analysis basic command after each load case, followed by the change command. The change command is not mandatory to use. Even if you forget to use it, the program will automatically insert it in the analysis. But you get a warning message in the output file. Okay, so now we run this analysis. You can now see the loads are applied in steps. 100% of loads are applied, and you can see the cable case converged note. So you should not use the results when it reports the cable case as failed or cable case not converged. We can now see the deflection diagram and support reactions. I noted down these values, support reactions, deflections, and you can see the static check may not match. The applied load and total reaction may not be equal exactly. The difference will not be exactly 0. Some small values will be always there. This is okay for nonlinear analysis, okay, but not okay for linear analysis. For linear analysis, you have to make sure that the static check is matching exactly. Okay, now let's have a look on this member and forces. You can see the axial force is 11 kilonewton on the cable member. Now I'm reducing this initial tension from 7 kilonewton to 1 kilonewton. Okay, just to explain you that there are multiple solutions possible. Okay, you can see that as soon as I reduce this initial tension from 7 to 1, you can see the cable iteration limit exceeded warning appears. Case failed. Okay. So then I cannot use the results. Okay. You can see these warnings. You can see it failed around 95 after applying 95% of the load. So in this situation, you may use the K small parameter, but you may, if possible, you may increase the initial tension or start using the stability parameter. Note that in this example, we have not used the stability parameter at all. We just use the basic performance cable analysis command. Okay, so now I start using the Sag minimum and stability parameter. Okay. For small models, I start with 0.1. Then once you try out with few projects, once you gain experience, then you easily come to can easily come to a decision about these values easily, just with few projects. Okay, so now I copy and paste this value, sag minimum of 0.7 and stability of 10, 145. Remember the stability parameter, I can use any value between 0 and 1000. Okay, the stability parameter unit is force per length. The sag minimum is a factor. Okay, any value between 0 and 1. The default is 0. Okay, and the initial tension, I leave it to 1 because sometimes you may not achieve higher initial tension on the cable on the site. So I leave the initial tension as 1 and I start using the sag minimum parameter and stability parameter. And now I can see the cable case converges. So with this example, I explained to you that there are multiple solutions possible, either by increasing the initial tension on the cable or by playing with the sag minimum and stability parameter in the model. Now we can see the results, the deflections. The deflections are higher compared to the linear cable analysis because the initial tension is lower now. Remember, for the linear cable analysis, we used initial tension of 7, whereas here we reduced it to 1. That's why the deflections are more. Let's filter our results to our cable members. And you can see the maximum axial tension is 10.5 kilonewton. Axial tension on the cable. Okay, now I'm going to open up another model. It's the same model, but just the load cases are modeled using load groups instead of repeat loads. So you can see the definitions. I have used the reference loads instead of repeat load. And you can see the number of primary load cases are reduced now, because when you use the reference repeat load command before, you need to model unrealistic load cases like wind load, and we need to analyze for those unrealistic load cases also, isn't it? That takes time. So that's why using reference loads is a better way, is a best practice, I would say, because you are analyzing only for real load cases like dead load plus wind load, and dead load plus wind load plus appurtenance wind load. Okay. And notice the perform cable analysis has been repeated for all these 3 real load cases. And we run the analysis and make sure the cable case converge. And let's check the deflections, 217 again, because the initial tension is only 1 on the cables. If you increase the initial tension, then this deflection may reduce. So it all depends on how much is the initial tension that you can achieve at the site. Okay. Let's have a look on the reaction, and you can see the difference is not exactly 0. The difference between the applied load and total reaction is not exactly 0. That is okay for nonlinear analysis because of the iterative nature of the nonlinear analysis. Let's check the other results, such as axial forces on the cables. The initial tension, the axial tension on the cable is exactly the same 10.5 kilonewton. On that cable, the highlighted cable, you can see the forces are 0 because the wind loads are acting in the opposite direction. So that's why the cable is sagging. Okay, so that cable is having 0 force. You can see the wind load direction, and the cables that is taking the wind load is shown in blue color, taking the tension. And you can notice the output file is clean of any warning messages or any instability messages or any errors. You can see the cable case complete. 100% of load is applied. Okay, so that was the example for nonlinear cable analysis, where we use the same guide master example. And here's the comparison of results between the linear and nonlinear cable analysis. For comparison's sake, I take the values with both the models having same initial tension of 7 kilonewton. Okay, so after modifying the initial tension after keeping this as constant for both the models, linear and nonlinear, then this is the tabulated results of deflection, axial force, and reactions. So you can see the deflection alone is 8.5% difference between the linear and nonlinear. Otherwise, the axial force on the members, the maximum and minimum axial force is exactly the same. So the difference is 0%, and the reactions is just varying slightly, only 3% difference. So what do we understand from this example is that for small structures like this, which is having few cables, it is okay to use the linear cable analysis. Okay, you may not need to do a nonlinear cable analysis. Okay, you will get only small difference in results. But where is the exact application of nonlinear cable analysis? Let's move on to this next example 3, catenary cable, nonlinear cable analysis. Okay, so here the cable is modeled as piecewise linear segments connected to create a curved profile, the sagging of the cable. Once you are able to solve this problem with a point load located anywhere on this, or a uniform load, or both, then you would be able to analyze any complex cable state bridge. Okay. So let's have a look on this example. So this is 150 meter span catenary cable. And the property, we just use the axial, the cross-sectional property only. And the initial tension we used is just 1 kilonewton. And the loadings in this model is 2 load cases. One load case is a point load, another load case is a uniformly distributed load. And we analyze it, we got some warnings. And you can see all the deflection diagram is all haywire, and the deflections are in kilometers. Okay, and the static check doesn't match. There's the total applied load and the reactions differ a lot. And the output file will be full of zero stiffness warnings, okay, as well as instability warning. Instability warnings are dangerous. That's where we need the engineer to go through this warning messages and make sure we understand it, then troubleshoot it. So the reason for all these errors is because first I tried to analyze it as a perform analysis, a linear cable analysis, which couldn't able to solve it. Then I replaced that command with perform cable analysis command. Okay. So using the editor, I can inactivate or delete the perform analysis command. and I rerun the analysis. You can see the cable out of balance. So case failed. The output file is full of warning messages. Now we start using the stability parameter and sag minimum parameter. So sag minimum, I'm going to use 0.9. After trying from 0.5, 0.6, then I arrived this 0.9. And stability parameter, I use 1. Starting from 0.1, I tried already. So I arrived at this value of 1 after trying out from 0.1, 0.2, 0.3, like that. Okay, so we just have these two load cases. The first load case is a point load. The second load case is a uniformly distributed load. Okay, and now you can see the results, the analysis results. The cable out of balance error message again appears. So this parameter doesn't work. So I'm going to modify this now. So I'm going to increase this value of stability parameter from 1 to 10. And if this value works, I may reduce it halfway for the next try. So you can see with the value stability parameter of 10 kilonewton per meter, this analysis converged. I can see the deflection results is nearly 1 meter, more than 1 meter. And you can see the sagging profile of the cable for the first load case and for the second load case. You can see here, this is a point load and how the right side portion of the cable lifts up due to this point load. And this cannot be analyzed using a linear cable analysis. This requires nonlinear cable analysis. We can have a look on the output file. The output file is clean without any error messages or warning messages. Make sure the loads are applied 100%. You can see the steps on the left side and the percentage of load on the middle and the iteration on the right side. So for each load steps, the program is iterating for convergence. So in 145 load steps, 100% of load is applied. And again, for the second load case, you can see the cable case converged. This is a 2D example. So STAAD plane command. And notice that as I explained in my few slides back, when any value works, I try to reduce it halfway for a better solution. Because this stability parameter is an artificial stabilizing stiffness matrix value. So this is going to alter the stiffness of the structure. Even though it reduced to 0 at the final iteration, for the initial iteration, it is going to use this stiffness matrix. So that's why it is recommended to use the least value as possible. So even though the value of 10 worked, I still reduce it to 5, and that also worked. So since 5 worked, I'm going to try even a smaller value, say 2.5 or 3. So this is how you iterate, you do a trial and error to get the correct solution for your model. So you can see cable case converged. So I'm doing the reverse way. From initially, I used a value of 1, and then I used 10, and then I used 5, and now reduced to 3. You can use from 0.1, 1, and then 2 and 3, the other way also. So there are multiple solutions. So you can see that now I reduce it to 2. you can see now it fails. Okay, the first load case failed, the second load case passed, converged. Okay, so I need to go back and change the stability parameter. If possible, we can increase the initial tension of the cable on the top, but let's try with a value of 2.5 only for the first load case, because the second load case already converged with a value of 2. So you can see with a value of 2.5, the cable case converged, okay, for the first load case. So we can now rely on the results, okay. So the deflection, maximum deflection is 1.3 meter approximately. The output file is free of error messages or warning messages. And hope this example gives you a clear idea of how to start from the basic command using perform analysis and then getting the wrong results, and then we started using the perform cable analysis, and then we converge. And notice that we can even change this model type from STAAD plane to STAAD truss, because all these members are cable members. There's no frame members in this model. There's no bending member. So STAAD truss command also will work. But in this case, the first cable, first load failed, the second load passed. So we may again try changing the initial, the stability stiffness matrix to a higher value and try it again. So why I'm doing all this iteration is just to explain you that there are multiple solutions possible. Okay. So now we can see just slightly increasing the stability stiffness matrix from 2.5 to 3, the cable case converged for first load case. And the deflection is same like last time, 1.3 meter. Large deflection. Okay. So this example is a good example for nonlinear cable analysis, having catenary cable. So this cannot be solved using linear cable analysis. Now we can have a look on this axial forces diagram, and we can annotate the value also. So that is 68 kilonewton axial tension. Okay, so hope that example explains you how to start using the nonlinear cable analysis. A small example, but it's a very good example for nonlinear cable analysis. Let's move on to the next example on lifting analysis, which is also using nonlinear cable analysis. Few notes. Traditionally, many users use a fictitious lateral support while doing the lifting analysis using linear analysis and adjust the lifting point or lifting lux position until they get zero or near zero reactions at the lateral support. This may turn out to be a lengthy process, as it is a trial and error method. The lateral support is used to avoid the instability issues while doing the linear analysis. With the nonlinear cable analysis, we can eliminate the need for the lateral support, the artificial fictitious lateral support, and can analyze without instabilities. This way, we allow the structure to sway during lifting, and if the sway is allowable, we can proceed without iterating the location of the lifting point and lifting lux. If the sway is not allowable, then we have to adjust the lifting point or lifting lux and reanalyze. Note that this is a large deflection problem without the lateral support. So when the center of gravity of the loading and the center of the gravity of the geometry doesn't match, when you lift the platform, it will sway. Okay. So that's why many users use some lateral support to avoid instability messages in the linear analysis. Okay, so let's quickly go through this video on lifting analysis. So this is a 16-meter span platform. You can see the lifting point is on the top with just a hook point only supported by Fy, only in the Y direction. And the sections I used are channel sections for the platform, 30 mm rod for the lifting slings. I sections also are used. And the loads are modeled using reference loads. So for lifting analysis, you have to use reference loads. Otherwise, you can model one primary load case with all the real load cases in it. Okay. Don't analyze this lifting analysis for unreal load cases like wind load acting alone. The structure will never converge. That's why I use reference loads to model my loads and then call those load cases to create real primary load cases and analyze this as a nonlinear cable analysis. So you can see the cable case converged. And here you can see the deflection. And notice that even the hook point, the lifting point also will deflect because it is not a pin support. It is fixed but release all except Fy. Okay, and you can see the platform is deflecting downwards as well as laterally. And make sure this deflection is reasonable and it is allowable in the site. So maximum deflection is 105 millimeter. And the displacement is in both vertical as well as lateral direction. So now you can see the animation of the deflection. Make sure this is allowed in the site. Okay, 100 and few millimeters. Okay, here's a support. You can see I released all except Fy. It's a fixed but support command. And the deflection we already checked. And here's the bending moment diagram. So we need to design this platform for even this lifting load also. And here's the axial force on the cables, all showing in blue color, meaning tension. The output file showing the center of gravity. I use this print CG command. And notice that the output file is clean of warning messages and errors. Okay. Very important is that your output file should not have any warnings or errors. Okay. You should solve those warnings before you start relying on the results. Okay. So notice that this lifting analysis, we analyze it easily without using any lateral support by employing the nonlinear cable analysis. Let's move on to the next example, the final example, tension rod system. This tension rod system consists of many cable members connecting to each other. So in this example, there are 3 disconnected structures. Okay. The span of this top roof is nearly 16 meters. This is a crematorium inside a concrete building. So the concrete portion of the model was not modeled in this structure. So we modeled only the steel members here. So let's have a look on this example. Okay, so you can see all the members are declared as cable, except the vertical members, which is a truss member. And these cable members are 16 mm rod section. You can either use the Dutch profile rod section database, or you can use a pipe section with internal diameter, same as internal diameter as 0. And here you can see the member truss and member cables. The initial tension on the cables is 1 kilonewton. So the loads on these examples are dead load, live load, and temperature elongation and temperature contraction. Note that the live load, temperature elongation, and temperature contraction are not real load cases. That's why it is very important that you use the reference load command to model all those primary load cases and call those loads in your primary loads to create real load cases, real load combinations. Dead load is the first load case. Dead load plus live load is the second load case. Dead load plus live load plus temperature elongation is the third load case, and so and so that you don't spend time in analyzing for unreal load cases like temperature load acting alone, which will never converge. Okay, so the temperature variation for this example axial for the axial elongation is 50 degrees Celsius change in temperature, and that will cause problem in analyzing the structure. Okay, so you need to employ this perform cable analysis and model real load cases to solve this problem. If you don't employ reference load cases, you'll end up in problems. If you don't employ perform cable analysis, you will not be able to solve this problem. Okay, so you can see the cable case converged for load case number 1, for load case number 11, which is the combination of dead load and live load, load case number 12, load case number 13, load case number 14. So I already did some iterations and I solved this problem. So don't want to waste time in showing you all the iterations, all the trial and errors. So you can now see the results. 83 millimeter deflection, maximum deflection, support reactions. And the statics check may not tally exactly because of the nonlinear analysis. That is okay. And here you can see the axial force on the cable members. And we can plot the axial force diagram. The blue color members are the tension members, the red color members are the compression members. So you can see in this model, almost every member is a cable member, except the middle member, the vertical member, that is a truss member, that is shown in red color, taking compression. For the roof truss is the vertical member. For the side structure, it is the horizontal member. We can annotate this axial force, and here you can see the axial force on this tension cable member. The maximum I would see is 9.5 kilonewton, 9.8 kilonewton somewhere. Okay, so the warnings is about the disjointed structure that you can safely ignore. And notice that the model is analyzed using the STAAD truss command. Okay, because all these members are either cable member or truss member. So we don't need to analyze it as a space frame. Just truss is good enough, STAAD truss. That way we can avoid many zero stiffness warning messages. Okay, and you can see the output file is clean out of any warning messages or error messages. 100% of load is applied at the 145th load step. Okay, so we have gone through one example for the linear cable analysis and 4 examples for the nonlinear cable analysis. And this nonlinear cable analysis can be used for almost any type of structures that has cables. On the screen, you can see a lifting analysis of air cooler using a spreader bar in the middle. On the left top, you can see the roof, the membrane sheeting roof with cables, catenary cables. On the left bottom, you can see the bridge, the cable straight bridge, having many cable members. On the right side top, you can see the burner boom on offshore platform. So supported by cable. It will be subjected to wind load also. So this requires a nonlinear cable analysis. And then you see the multi-point lifting and the roof of a stadium connected through cables. Okay, so all these are other examples of nonlinear cable analysis. To summarize our presentation today, cables by nature are geometrically nonlinear because they sag in compression and stretch in tension. We can approximate the nonlinear nature of the cables into a linear cable up to a certain extent, provided the structure is simple with few cables, just like our example 1 today and example 2. Example 1 and 2 are exactly the same guide mast. Example 1, we analyzed using linear cables. Example 2, we analyzed using nonlinear cables. And we noticed that the change in results is negligible. Okay, so when the deformation of the structure is large, as in the case of our example 3, 4 is a lifting analysis, so it was swaying, definitely large deflection. Example 3 is a catenary cable, so the deformation is large. Okay, or when there are many cables, as in the case of example 5, or tension rod system in the structure, or the geometries of catenary cable, just like our example 3, catenary cable, it is recommended to use the nonlinear cable analysis. Hope I summarized this presentation today well. So please subscribe to our YouTube Bentley Structural channel. We have lots of videos there posted every day. Utilize our LAN server. We have on-demand trainings for all our structural products. And we have some live trainings as well, live instructor-led live trainings. These trainings are available free for our Bentley Select users and for a fee for non-select users. Okay. So at the end of the training, you can print the certificate as well. Please utilize these trainings. For support, there are various methods of getting support from Bentley. The easiest way is to post in our community's forums or raise a service request or utilize the Connect Advisor, which opens up every time when you open any of our structural programs or Bentley programs. So now that we have finished our presentations, before we move on to the question and answer session, I would like to have few polls. I want you to get engaged. Now that you have learned the use of nonlinear cable analysis, will you be using this feature in your future projects? So I'll give you 10 seconds for answering this. Please answer yes or no. At the beginning of the presentations, I noticed that many of